Okay, today's first half of lecture, we're not going to have a lot of new content in terms of mathematics. We're just going to introduce a lot of terminology that you should get comfortable with and that you're probably going to hear a lot in the future in your career. So we're going to talk a lot about different names that we give to the responses of circuits. So that's kind of basically what we're going to do. Before we do that, let's review what we said in the previous lecture. So in particular, we said that when the initial conditions are 0, we can replace in the Laplace domain an inductor by an impedance CL, which equals Ls, which in this case would be 1 over 2S. And for a capacitor, we can replace it with an impedance ZC, which in this case would be 1 over 2S, which is 2 over S. Additionally, if we have non-zero initial conditions, we derived some models for the circuits involving both the capacitor and inductor, and we basically added sources to incorporate the initial conditions. So if we recollect, in this particular case, let's say we wanted to use the parallel models. If we recollect, we could, for this one, let's say we want to use, the parallel models, let's just say. So if we recollect, the parallel model would involve a current source along with your impedance. And then what we said is, let's say this is the I for the either inductor or capacitor, and this is Z for either the capacitor or the inductor, doesn't really matter. Then you're going to have a current source that for each of these two types of elements is going to be different. And the way you derive this current source is by basically deriving the two equations. So you have I, L comma C has to be equal to kind of IS. Well, in this case, it's got to be equal to, let's say this is the voltage here, VLC. So VLC, so this is plus minus divided by the impedance. So whatever that, whether it's an impedance of a capacitor or an inductor, minus IS for the capacitor, or sorry, inductor and capacitor. And then we had another equation which said that VLC has to be equal to, so here I'm putting the comma L, it's either an inductor or a capacitor because we're deriving the same topology for both of them, has to be equal to the impedance CL or C times the total current going through there, which would be equal to IL comma C plus I source. And then what we did to figure out what I source was, we just basically used our IV relationships for the capacitor and inductor in the Laplace domain. So we said that the capacitor, we have that the capacitor current is equal to C S V sub S, so remember I sub S, minus V0. And so for the capacitor, we would want to use this equation. And so that's going to give us that ISC equals C times V0. And we already know the impedance is just 1 over C. So ICC is equal to 1 over SC. And then for the inductor, V sub S equals L S I L sub S. Here, let me just say C minus I L sub 0. And then we can use this this equation for this one. And so we're going to get that the impedance is S times L. And the source is actually ISL is actually negative ILs of 0 divided by S. Okay, so now what we can do is to replace this circuit, we just simply use a parallel configuration which involves the inductance, and now we just add that current source, which if you assume that the voltage goes from here to here, VL, has to point in the opposite direction, and it's going to be ILs of 0 over S. And then for this capacitor, we have to add a, so this should be 1 over 2. So this becomes 2S. This becomes, what is it? S over 2. And then this gets a current source which points in the direction of IC. So this way. And it's got a value of C times V0. And so if you have initial conditions, you kind of, this is what your final model will look like. You can either learn how to derive these equations on the fly or memorize the 4 circuits configurations. It doesn't really matter. I have terrible memory, so every time I do this, I just re-derive it. It's not that hard. But yeah, so then we said once we have this, we can solve this in the Laplace domain, take the inverse Laplace transform, and then this, of course, would be 1 over S squared. And then we could actually analyze the circuit. Okay, so that's kind of what we learned in the previous lecture. So basically, when you have non-zero initial conditions or 0 initial conditions, how to solve these circuits using Laplace domain techniques. All right, so now we're going to actually define some names that we give to different parts of the response of a circuit. So the first thing we're going to define, which we've already kind of alluded to earlier, which is the zero input response. And the zero input response basically means the response of the circuit if you assume that the source has been removed. So, removed. In the case of a voltage source, to remove it, you typically assume 0 volts across it. So as a result, it behaves like a short. And in the case of a current source, to remove it, you typically assume 0 amps across it, so it becomes an open. Now, to find the zero input response, you would basically take this circuit and then you would add the respective current sources. So basically, this would be this would be ILs of 0 over S. And then here we would have one pointing in the same direction. And this one would be VCs of 0. And that was times the capacitance, if I'm not mistaken. So basically, you would just use the circuit models we derived in the previous lecture. Yes, and it is times the capacitance. Yeah, so you would analyze this circuit in order to get what the zero input response is. And in both cases, so in this case, it would actually have a current source driving this thing this way. ILs of 0 over S. And we actually analyzed this circuit in the previous lecture. Notice that I'm writing the parallel configurations. It's actually easier to analyze this circuit using the series configuration. So I wouldn't actually do this, but I'm just trying to imply that what's driving the circuit is the initial conditions when you have a zero input response. So just to reiterate, if you're ever asked for the zero input response, you're going to remove the inputs from the circuit and you're going to use initial conditions to drive the circuit. And then we have what's called the zero state response, and zero state response is basically the solution to the circuit assuming 0 initial conditions. So in this case, whenever you ask for a zero state response, you replace the capacitor with 1 over SC, and you're going to replace the inductors with S times L. So the zero state response just means that the circuit is in a zero state, meaning all initial conditions are zero. So basically, you have two cases. Either zero input response, sorry, means that all sources are zero, so there are no inputs. And then you have zero state response, means that all initial conditions are zero. In general, you can always assume that the solution to a circuit will always be the sum of the zero input response plus the zero state response. So you can always break up your problems into two problems. So here, for example, we're being asked for the zero input response. So what we do is we replace the source by a short. And now we use our initial conditions to drive our circuit. And so this is actually the same circuit from last lecture. So here is the same derivation that I went over in the last lecture. And you can come up with the solution for this particular circuit. If you assume that IL is 1, then this would be cosine square root of 50t. And VC equals 2, then you have 5 over the square root of 50 negative, which is what we assumed in the previous lecture. So once we have the zero input response, we can actually then solve for the zero state response by simply assuming zero initial conditions. So that's what we're going to do next. So for the zero state response, we would actually replace this circuit with an impedance 0.4 S, and then 0.05 S, 1 over 0.05 S. And then this would be replaced by 1 over S plus 3. And we actually, again, solved this circuit in the previous lecture. So you could actually solve this circuit to determine what the zero state response. And so here's the solution that we got last time. Now, as it turns out, once you solve the circuit assuming zero initial conditions and zero input, the solution to the full circuit will always be the sum of the zero state response and zero input response. So if we wanted to get the solution basically to that the complete solution, we would just add the two of them. And that's basically why this is interesting. In an exam, you might be asked for a zero input response, so you need to know that that just means that's lingo for remove all the inputs. Or you might be asked for a zero state response, and that's lingo for all initial conditions are zero. So you just need to know that for this lecture. Of course, for the previous lecture, you need to know how to actually solve it. Okay, so we have another way to decompose our solutions. So we typically refer to our responses as either steady state or transient responses. The steady state is a solution that basically continues up to infinity, or doesn't go to zero as time goes to infinity. So the steady state will always be either a sine or a cosine, sine or cosine, or a constant in time, which you can think of as a cosine with frequency 0. That's what we would call the steady state response. As it turns out, when you did phasors, what you were actually looking for was the steady state response of the circuits. So you already have some experience with the steady state. The transient response is all other responses, but in particular, kind of the more correct definition is any response that goes to 0 as time goes to infinity. So any response that decays to 0 as time goes to infinity, that would be called the transient response. So when we did our RC circuits connected to DC sources, and then a switch, and let's say we had a resistor. Let's put a capacitor here, whatever. Here, hold on. Let me just rewrite this. So we had a resistor, and then we put a capacitor here. If you recollect, this circuit, after a while, if I were to look at the voltage across the capacitor, VC, it should be equal to 5 volts. And let's just assume the initial voltage on the capacitor was 0 at time equals 0. So that the voltage is actually going to go from 0, and then eventually it's going to reach 5. In this case, that solution, which this would be kind of an exponential part, this part of the solution, which is actually varying, which would be e to the negative 5t, 5 times e to the negative 5t, that's what we would call the transient response. And I hope you're enjoying your eyes are enjoying the bright yellow. That's just the color that fell. I'm sorry. And then this part here is actually equal to the response. The 5 is actually would be what you would call the the steady state. Steady state. So essentially, when we analyzed all these circuits, we always found this I infinity. For these switch circuits, I infinity is actually the steady state. And then everything else, which typically is going to be a decaying exponential. This shouldn't be 5t, it's just some t over tau. Sorry. Here, let me use a different color. I'm not going to be mean. This is what we would call the transient response. In engineering, we don't like this. We don't like this. In real life, we actually like this because we're like a chemical reaction that never reaches that steady state response, which would be kind of like our death. So our lives are very transient. Like they only last a fixed amount of years, and we hope not to get to that steady state. But in engineering, we don't like we don't like transient responses, and we're always trying to keep them as short as possible. One thing you can think about is the preheat on an oven. Let's say you want to make a cake. You know, you have to wait roughly 15 minutes before you can that oven gets to the terminal temperature. So if you look at the temperature as a function of time, so let's say you need it at 350, and then after 15 minutes, so you turned on the oven here, it's going to slowly go up in temperature, and then it's going to stay flat. Before you can put in your cake. So typically this takes 15 minutes. Of course, chefs out there would love it if you can actually do this in 1 minute. So this transient response is something we don't like in engineering, basically. We typically want to engineer out the transient response. We want things to react very quickly. Once we push that button, we want it to be on, we want it to be ready to go. So that's what basically a transient response is. And then there's kind of another decomposition, which is the natural and forced response. So if you looked at our previous circuit, we had kind of a source, 1 over s plus 3, or e to the negative 3t. Then we had an inductor, and then we had a capacitor. And in that case, typically the forced response is whatever response is of the same form as the sources. So when we were analyzing circuits in the beginning of the semester, what you would consider the force response would be that particular solution that you came up with. And then the natural response is everything else, which is also, the natural response also is associated with the solutions to homogeneous equation. That would be the natural response of the circuit. As it turns out, for linear circuits, you can never get anything out other than the homogeneous solutions or something of the form of the force response. So those are all the decompositions. Now I will go over an example. Okay, so let's look at this circuit. So it's asking us to find the Laplace transform of the zero input response. So what do we have to do to the input? Well, we have to zero out the input, which in this case, it would mean if we assume this is 0, this behaves as an open. And so what is going to drive this circuit is the initial conditions. So we're going to have kind of a resistor, R, and then we're going to have an inductor, SL, and then there is a current source, which is I0 over S, and then we're going to have a capacitor, which is going to be, well, here I'm just going to make this into an impedance just to emphasize that it's an impedance of 1 over SC, and then we're going to have a source associated with the capacitor that it's going to be C times VC sub 0. So to find the response, we simply can just say that we can apply KCL at this node. And so we're going to have that VC over the impedance of R plus 1 over SC. Oh God, what am I doing? Here, I'm going to just not skip steps. VC over R, which would be a current going this way, plus VC over SL, which would be a current coming this way, plus I0 over S, plus, which would be the current going through this branch, and then you have plus SC VC, which is the current going through this branch. So 1 over SC is just SC, and then minus C VC sub 0 equals 0. And then what we can do is just move all the initial condition related quantities to the right hand side and divide out and factor out all the things multiplying the VC factor. So in this case, we're going to have SC plus R plus 1 over SL times VC equals I0 over S minus CV sub 0, VC sub 0. And then we can divide both sides by this factor. And so we're going to, and multiply, and okay, VC sub 0, VC sub S equals I0. I'm going to multiply this top and bottom by S to make it look better. SC VC sub 0 divided by S squared C plus SR plus 1 over L. So I divided by this factor and then I multiplied the top and bottom by S to make it look prettier. I could have also divided by C, which I'm actually going to do that to make it look even prettier. C R over C, and so I have to divide here by C. Not yet. Okay, so that's basically our zero input response in the Laplace domain. We can inverse Laplace it, and then we can get our solution. So here's kind of that derivation done again. So in particular, we replaced the capacitor with a current source. and the inductor with a current source in parallel to an impedance. So in an impedance and an impedance. Okay. Yeah, so that's the zero input response. If we wanted to find the zero state response, it would be a lot easier. We would just simply replace the inductor with an impedance, and then the VCs of S is actually just equal to I-ins of S times R in parallel to SL in parallel to 1 over SC, and that's just equal to I-in of S divided by 1 over R plus 1 over SL plus SC. And then we can multiply by S and divide by C. So we're going to get S I-ins of S divided by C. And then we're going to get the S squared plus S over RC plus 1 over LC. And that's it. Did I do this correctly? I did it correctly. Yeah, I did it correctly. All right. So here you go. That's what we got. And so that's our solution to this particular circuit. Okay, so we got our zero input response and our zero state response. And I have a feeling I messed up on the previous slide and I put this R in the numerator in one of my algebra steps, but it's correct on the typed up slides. Okay, so yeah, okay, so that's the zero input and zero state response. Now, if we plug in some numbers and we assume that this is our input, we can actually solve for VCs of t. So that's what I'm going to do in the next slide, and that just involves doing an inverse Laplace. So here's kind of the zero state response. Here's and so I can split that up into coefficients. We already know A0 is 0 because remember that whenever this polynomial order is lower than the denominator one, A0 will be 0. S plus 3 coefficient can be found in the usual way. And then we can find the S plus 1/4 squared coefficient in the usual way. And then to find our last coefficient, we can just apply 0 and use the fact that A0 is 0 to get the value for our coefficient. In this case, I actually evaluated for A0, so I had to choose another value of S. And then basically then we get our solution. So this is just a lot of arithmetic, and I'm not going to spend a tremendous amount of time doing it. You should probably try to do this on your own and make sure that you can actually recreate this at this point. If you can't, you should go back to the inverse Laplace video and try to understand that better. Okay, so we can find the zero input response the same exact way. And so once we have those two, we can actually combine the zero input response with the zero state to get the total response, which is what the prompt asked us to do. Okay, so that's basically it. Now, if we were to change the different initial conditions, what we would have to do is just solve the circuit again, but we would only have to solve the zero input response because the only thing that changed was the initial conditions. So that would save us a lot of time because we wouldn't have to solve for the zero state response again. We would only have to solve the zero input response and then just change it. Same thing, if you change the source, we don't have to solve the zero input response anymore. We just have to solve the zero state response. And then we just change that part of our solution. So that's kind of why this stuff is fairly useful. Yeah, so let's look at one more example. So here's an interesting one. So it's telling us to find ILs of 0 and VCs of 0. So for this particular case, we have that a circuit is opening at time equals 0. And so for time less than 0, we have that the circuit looks like this, 10 volts. And then I have my inductor, and then I have my 1/30, and then I have my capacitor. And you have to remember that inductors behave as short after a very long time, and capacitors behave as open. So we're going to have that the current flowing through here will actually be 10 divided by 1/30 ILs of 0 minus, and that's just going to give us 300. And then 300 amps. Oh, wait, sorry. This is not 1/30. This is 10. So 10 ohms. So this should be 10. Yeah, that makes more sense. I'm like using big numbers. 1 amp. And then the capacitor behaves as an open, so there's no impedance associated with it. Now to find the voltage drop across here, well, that's just going to be 10, because remember this behaves like a short. So VCs of 0 minus will be equal to 10 volts. So now we have our initial condition, and that's what's going to drive the circuit for time greater than 0. So now that we have our initial condition, we can use Laplace techniques to analyze this circuit. So to analyze this circuit, we just simply replace the inductor with a impedance and a voltage source in series. Does that make sense? Or should we use a current source? What do we think we should do here? Here we should probably use a current source. So let's just put a current source here. So we know that the current source has to point up, and it's just C times V, C of 0. So it's just going to be 10 divided by 30, which is just going to give me 1/3 amps. And additionally, this would just be 1/SC. And then we can replace the inductor with the series configuration. So just so that I can recollect, if we have our series configuration, it's going to be an impedance and then a source. So CL, and then we have IL, LDI, LDT. So no, VL equals L S times ILs of S minus ILs of 0. And then for this particular circuit, if we assume that this is minus plus VL, and then we have plus minus VL, and then we have our current IL moving in this direction, we're going to have, and then this is VS, we have that VL equals ILs of S, so it's equal to ILs times ZL plus, right? Yeah, plus VL plus VS. So basically the voltage drop across here plus this voltage would be equal to the total voltage. And that's the negative terminal, so it should be minus VS, sorry. Yes. Okay, so that gives us that VS in this particular case should actually just be L times ILs of 0. Okay, so we have here, we can replace this with an And as you can see, I haven't really memorized these, so I have to derive them each time. You can just memorize them. I just don't have a good memory, and that's what works for me. But you got to do you. And I feel like for a lot of you, you're in the same boat as me, so it's good to just see the derivation a bunch of times. And then you have here L, IL, so 0. And so now we can just multiply that by L, and so we're going to have 15. 1, 5 volts. Okay, so since this source has been disconnected, I'm just going to treat it as ground to make things look simpler. So now our equivalent circuit is just basically, you have ZL minus plus 15 volts. Then you're going to have a 10 ohm resistor. And then you have in parallel 30 over S, and in parallel 1 over 3. And then this should be S times L. So now we just need to analyze this particular circuit, and then we're going to be done. So let's just say we were to apply KCL here. So we're going to have negative 1 over 3. I'm going to call this Vx plus 30, or sorry, S Vx over 30 plus Vx over 10. And then in this case, it's going to complicate things because we have a source there. So we're just going to call this IL plus IL, sorry, minus IL equals 0. And I made a big mistake, big mistake. Because, as you can see, analyzing the circuit is quite complicated. So I'm just going to go over the solution in the next slide. Yeah, so basically you can, and I have a feeling I didn't even go, you can just use these circuits, and we derived this one in the previous slide, LDIL dt. Let's see what I did. Oh, I only asked for the 0 state response because actually finding the 0 input response is quite hard. Anyway, yeah. So basically, after I made you derive these initial conditions, I didn't actually make you solve it. And you can see why, because you saw how ugly that circuit got. So here it is. And then this is going to find the 0 input response. So now you can solve the 0 input response. And here's the 0 input response. So, okay, so one lesson that you can see from this, if you pick the wrong configuration, things look very complicated. The right configuration would have been to pick this one as the parallel configuration too. But as you can see, that looked very difficult, whereas this actually is quite simple to solve. So just as a recommendation, if the circuit looks too bad, try another representation until you see one that looks good. So it's good I kind of got stuck on that, because now you get an idea of what to look for. I'm skipping a lot of the math here because it's actually very tedious. I do think you should try to go over these examples on your own. I don't think it adds much at this point. You kind of get the idea. You take your circuit, you convert it to the Laplace domain, and then you deal with everything as if it was a resistor network. So you use your good old 2K1 skills to solve the circuit, basically. Okay, so here's kind of the final solution. and I'm gonna move on to the next part of the lecture because otherwise I'm gonna run out of time.